Okay, so everybody settle down, please. And because I'll be with you for the next 3 days, talking about magnetism. So first of all, I would like to know a little bit about the audience. So everybody here has done MSc, right? Yes. And how many people are from outside Hyderabad or outside this university? Okay. So the audience is mostly people who have just finished MSc and people who are beginning to do their PhDs, right? Is that correct? So I wanted to get this information because I will assume that you know certain things. I mean, the point is, you see, is it okay? So I'll assume that people are already familiar with certain sort of basic things. And on this board, I'll write down some of these things, topics that I'll assume that you already have seen, which I'll not sort of spend a lot of time explaining. And then, if it turns out that it is not really correct that you have all seen this, then I can spend some time on those topics also. So this I'll keep on the board. What prerequisite? First of all, this whole course is about magnetism, so I'll assume that certain basic facts about magnetism you are all familiar with from your E&M courses or very elementary facts. Like so, I mean, which is called magnetostatics. And here the elementary things are like you have this B and H fields. Vector potential. Elementary things about magnetic moments and things like that. So is it okay to assume that you have already seen these things and I don't need to really talk about these things in this course? Yeah? Then since we'll be dealing with some statistical description of magnetic moments, some elementary things in statistical physics, I'll assume that you have already seen. Everybody has taken a course in statistical physics here? Thermo and StatMech? Yeah. So here, so people know things about free energies, partition functions, etc. So even today, I mean, when I start actually the lecture, then you will see that I'll be making use of partition function, how to get free energy from that, and from the free energy, how to get different thermodynamic properties by taking derivatives and so on and so forth. We'll also assume that you know some basic things in quantum mechanics. So here, elementary things like everything comes from electrons as far as magnetism is concerned. The fact that the electrons are fermions and they obey Fermi statistics, so that's going to be very important. There will be also some discussion of charged particle in a magnetic field and Landau levels and things like that. Again, I'll assume that that's something that you're already familiar with. So Landau levels. So I will assume that you have already seen some of these things. If there are many students who have not seen these things, then I would like, it would be nice if you can let me know. Then in subsequent lectures, I can spend some time on explaining those things a little bit more. Okay? So with that, let me start with basically the material that I want to cover. The material that I want to cover involves trying to understand macroscopic properties of magnetic systems from a microscopic description. So I'm sure all of you are familiar with, you played around with magnets when you were a kid. You have done BSc, MSc, many experiments where you deal with magnetic fields and things like that. So you're familiar with macroscopic sort of description of magnetic systems. But the point is, this macroscopic description comes from some microscopic physics associated with electrons, ions, and whatnot. So the subject of my course is going to be how to understand some of these macroscopic properties from a microscopic description. And the sort of methodology to be used is essentially statistical physics. You already know that that is what one does in statistical physics. If you have a gas, then you want to understand the macroscopic properties of the gas or a solid or a liquid, something like that, in terms of macroscopic objects, which are the atoms or molecules which are interacting. And then, the statistical mechanics allows you to connect the macroscopic behavior with this microscopic description. So we'll be starting with that. We'll be starting with basically what is the microscopic origin of magnetism. And of course, magnetism is just one word, but there are many different materials, for example, that one studies magnetism in. Many different kinds of magnetism, like paramagnet, then you have ferromagnet, then you have diamagnet, even in many other different kinds of magnetic materials which have different kinds of magnetic ordering. So that's basically going to be the subject of this 6 or 7 lectures that I'm going to give, how to understand those macroscopic behavior from a microscopic description of magnetic moments. So basically, all magnetic phenomena come from electrons. Electrons, in a solid, of course, we'll be talking about mostly solid magnetic systems. So we have ions in a solid, you have electrons in a solid, so carry magnetic moments, and the behavior that we see at the macroscopic scale arises from basically this large number of such electrons or ions, magnetic moments which are interacting with each other. So first of all, one needs to understand the origin of these microscopic magnetic moments. Electrons are charged objects, so whenever electron moves, there is a current associated with that. The current produces a magnetic field. That is something that you in this subject you have studied about that. Wire carrying a current or a loop of current and so on and so forth, and what kind of magnetic field that is produced by that. So I'll assume that you know about it. So electrons, of course, in a solid or in a hydrogen atom, for example, will have some angular momentum, and this angular momentum is associated with the magnetic moment of the electron. So basically, one source of microscopic magnetism is basically the angular momentum of the electrons. Since they carry charge, there will be a magnetic moment associated with it. Electrons also have spin. This is not associated with electrons going around in a circle or something like that. There's intrinsic spin variable, intrinsic angular momentum associated with the spin. So that also gives rise to microscopic magnetic moments. The point where one starts is basically something that tells you about this magnetic moment in terms of either the orbital angular momentum or the spin angular momentum. So this is what I'm going to do at the beginning. This is something that I'm sure you have seen earlier. So just to remind you, so we are talking about microscopic magnetic moments, dipole moments. And I will use this symbol mu to determine a microscopic magnetic moment. And as I said, this mu can arise from either orbital motion of the electrons or the intrinsic spin, angular momentum that the electrons have. So first consider the orbital this also fixes the notation that I'm going to use. There will be a factor of G. There will be something which is called mu B. There will be L. So what is this? G is called the Landé G factor, and for orbital part, G is equal to 1. I introduce this because later on when we talk about the spins, the G value will be a little different. So it's a good thing to keep it there. Mu B is called a Bohr magneton. And this is basically E times h bar 2 times mass of an electron. And L is a dimensionless quantity. It's an operator, but it's an angular momentum operator, out of which I have taken out the factor of h bar. So L is typically angular momentum operator L divided by h bar. So if you electronic charge, this is h bar, reduced Planck's constant, and this is the mass of an electron. So these things you know. So from that, given an electron in an orbital state where there is angular momentum L, then that will lead to some intrinsic magnetic moment that is given by Dasgupta. So why these things come into the picture? That is something that you should be able to tell from this. Basically, this picture is like this, that the electron is very sort of crude picture is like this. Electron is going around in an orbit. This is charge E. And charge particle motion gives you current. This is like a current loop, and the current loop will give you some kind of a magnetic dipole moment. And that dipole moment will be related to the angular momentum of the electron in that current loop. So everybody knows this. I mean, how to relate, for example, this is even classical. This is not, at this point, I'm not talking about quantum mechanics. Charged particle going around in a loop that will give you some magnetic moment. H bar appears here because I have taken out the h bar from the angular momentum. Why I have taken out this h bar from the angular momentum? It's just easy to deal with the algebra of angular momentum operators, always not having to write this factor of h bar. And in quantum mechanics, I forgot to mention that since we are dealing with angular momentum in quantum mechanics, you have to be familiar with the algebra of angular momentum operators. For example, what are the eigenvalues of L squared? What are the eigenvalues of a component of L and things like that? That also you have to be familiar with. Also, how to combine the angular momentum to angular momentum, adding angular momentum and things like that. So it's better to put this there. So this is of angular momentum operator. Okay, so this is just, so to speak, the definition of the magnetic moment associated with an electron which has angular momentum capital L. So this is one source of microscopic magnetic moment. I said also there is also a second source, which is the intrinsic spin of the electrons. So there will be equation like this, which will relate the magnetic moment to the spin operator now, not the angular momentum operator. So, so this is for, I actually put it like this, orbital and then there is also angular momentum associated with the spin, and there again you will have a mu G times mu B times, now we have the spin operator, and here the G factor is 2. That's the reason why one introduces the G factor. For the angular momentum, it's just 1, but when you're dealing with spin, then you have to put a 2 there, and little s is big S divided by h bar. Big S is the actual spin operator. and then divided by h bar to make it dimensionless. And so basically, these are the two microscopic sources of magnetic moments. And of course, I mean here, electrons are spin-and-a-half objects. So this S will be basically spin-and-a-half operator. Its just Z component will have only two values, plus a half and minus a half. So that comes later on. The next thing that I want to write down. So this is basically magnetic moment, macroscopic magnetic moment. And then what I want to write down is basically the energy of this magnetic moment in an external magnetic field, because magnetic field will come in most of the things that we'll be talking about. So basically, if I now have a magnetic field, and I use a slightly unconventional notation for that. I use this small h with an arrow to determine the magnetic field. Typically, we'll have the B, the standard notation typically is B, but all the things that I have done where it is called H, so this is the notation that you have to remember. So now I put a magnetic moment in a magnetic field, then the energy minus mu dotted into. Again, this is something that everybody knows, right? I mean, when you put a magnetic moment in a magnetic field, there is energy associated with it. The magnetic moment wants to sort of align in the direction of the magnetic field. So if I want to minimize the energy, then mu should be in the same direction as h. But they are not aligned, then of course the energy is somewhat higher, and you basically have this form. So if I now use these mu's, either this one or that one, in here, then we'll have something that looks like minus g times mu b is there and everywhere. G times mu b is there. And then you have h, and you have s z, where h, I am assuming that h is some magnitude in the z direction. So this energy is something that, it involves the z component of the angular momentum. In quantum mechanics, you know that if this S actually is coming from some L, then this Sz will have 2L plus values going from minus L to plus L. For the spin case, we are dealing with spin half objects. So this Z can only have two values, which are plus half and minus half. So this is one of the reasons that I am dealing with this dimensionless angular momentum operators. I don't have to worry about h bar. So these are just numbers. And h bar has already been taken into account in the definition of the Bohr magnetism. So this is the standard notation that I'm going to use. I'll keep this on this board. That I will not make a distinction at this point between whether I'm dealing with the spin part or the orbital part. I will in general write the energy that I have written down here. And this Sz then will be either a spin operator or angular momentum. It could be either integer. L, of course, takes integer values, whereas S takes values half, and there are more than one electrons, then there could be other half integral values. So in general case, there is a minus sign missing here. This Sz will take values from, so we have 2s plus 1 values, starting with minus s plus 1 all the way up to plus s. S can be either integer or half integer, depending on whether you're talking about just the orbital part or whenever also you mix the orbital part and the spin part, there is some spin orbit coupling, then the total angular momentum will not be an operator where this L is an integer. It will be half integer. So to keep everything general, this is notation that I'm going to use, that whenever there is a magnetic field and there is a magnetic moment, a microscopic magnetic moment, then the way that it interacts, it gives you an energy which is given by this, where this Z component can have 2s plus 1 values, and s can be either integer or half integer. Okay? So this is the microscopic, talking about a single magnetic moment. But of course, in a solid, or that's mostly what we are interested in, there will be a very large number of these individual magnetic moments, and the macroscopic behavior will come from this ensemble of magnetic moments, which when you have a magnetic field, then this gives you the energy associated with the magnetic moment in a field. In general, of course, when we talk about more complicated systems like ferromagnet or antiferromagnet and things like that, another part of the energy will become important, and that is the energy associated with the interactions among these magnetic moments. This is something that you already know, that from magnetostatics, that if you have two dipole moments, the dipole moments, of course, interact with each other. The energy of the pair of them depends on the distance between them, how they are relatively oriented, and things like that. So that's one kind of interaction, but in a solid, there will be many more interaction of these magnetic moments. So basically, the kind of problem that we'll be dealing with is where you have a full Hamiltonian, which will have some interaction part. This is the part that I'm just talking about, interaction of individual magnetic moments with in the presence of a magnetic field. And I have put in this label I here to say that I can go from 1 to the total number of such magnetic moments that you have in your system. And then there will be another part, which is the interaction between this spins or angular momentum, whatever you want to call it. I'll call them spins most of the time because short word, and also the magnetic moment can come from, as I said, both spin and angular momentum, but in general, I mean, I'll call them as spin. So the problem that, the things that I'm talking about is basically starting with a description that looks like this, that you have a system where there are microscopic magnetic moments, which are given by this formula, and they interact with an external magnetic field, and they also interact among themselves. And then the question is, given this, what can you say about the macroscopic properties of the system? That is going to be the subject of what I'm talking about in this code. So that, of course, is a difficult problem, because if this part is difficult to handle, because you know that interacting systems are always difficult to handle, because you have to treat the whole thing. You cannot treat them separately and then get the final result. You have to basically take into account the fact that one affects the other, second one affects the third one, etc., etc. So initially, I will start with a situation where I'll just ignore this. I will assume that you have independent spins, independent magnetic moments in a magnetic field, and then one tries to understand what kind of macroscopic magnetic behavior that system will exhibit. And when we many interesting things come interaction, so majority of my talk will be on the effects of interactions. But to begin with, I will assume that just because it's difficult to do, and I'll just look at this part of the Hamiltonian, and from that I'll try to figure out what kind of macroscopic behavior the system is going to exhibit. Okay, so you have seen this earlier. I mean, you have non-interacting spins. Then what kind of macroscopic behavior, magnetic behavior, you expect? So Somebody, some volunteer? No? Majority of you, if not everybody, has seen this. Thing that I wanted to sort of emphasize that this kind of, I'm giving lectures and so on, this is going to be useful when there is some interaction, some give and take. So you have to tell me a little bit about what you know and what you don't know, and otherwise, I mean, I'm at a loss as to what about and so on. How many of you have heard the word paramagnetic? Paramagnetism. Only so few? I mean, I thought, okay, so I'll talk about paramagnetism here. Curie law of susceptibility. Yeah? Again, show of hands. Okay, so it seems to me, I mean, I'm sure, majority of you have actually seen these things, but it may be that, we were too shy to tell me, or you have forgotten about it, or something like that. So, I mean, we have to start somewhere. So, I will then start with that. I will start with the simplest magnetic system, which is basically a paramagnet, and then try to see, what one can say. Paramagnet is just this. I have thrown out this part, not taken into account the interaction part. It's just the interaction of the spin systems with the external magnetic field. And the behavior of that will show certain features which you associate with what we call paramagnetic system. So what I think that it's coming on and off or something like that. No, I mean, you can continue to hear me sort of. That's good. So then the reason that I have kept it here because I will be using this later on, so I can erase this. So one macroscopic property that is very common and that sort of is very basic to magnetism is what is called magnetization. Magnetization is something that magnetic system only a magnetic system has. So I will call capital M the total magnetization. The volume of the system, and I will also use M. Magnetization divided by the volume of the system. Magnetization per unit volume. And this is an intensive variable. This is an extensive variable. But what is this magnetization? It is the total magnetic moment of the system. The system has some microscopic magnetic moments, mu, I was telling you earlier. So it's a thermodynamic quantity. So this quantity is sum over I goes from 1 to n, mu I. Mu I is the ith magnetic moment, and this brackets that I put is that we are looking at a thermal average. Why are we looking at thermal average? Because we are looking at a system at equilibrium. At equilibrium, the system does not stay in one microscopic state. It explores many, many different microscopic states with some probabilities that you know from statistical physics. So basically, when we look at some observable, average that observable over these microscopic states with appropriate probability. And that average process, I'm calling it this. This whatever sits inside is the quantity that is being averaged. So the problem that I'll be dealing with now is basically calculation of M as a function of magnetic field, as a function of temperature. And here we'll assume that the moments are not interacting with each other at all. So the Hamiltonian is just the sum of these interactions. Hamiltonian will be what I have written down there, but now minus G mu B magnetic field, and then sum over I. Okay, and do you know? I mean, given this Hamiltonian, how to calculate this average? Or in general, so I mean, if I want to look at the magnetization in the direction of the magnetic field, then I will have this. This will become then sum over I. Mu I will be something in front, and then is I. And if the external field is in the z direction, then I'll be looking at the z component of this SI and its average value. So there, this Hamiltonian will come into the picture, and given this Hamiltonian, given this Hamiltonian, does one know how to calculate this quantity at temperature T? So this is a sort of elementary problem in statistical physics, where you are given the Hamiltonian. These are the values. SIZ I told you about. We'll take this 2s plus 1 values, going from minus s to plus s. These are the different energy levels of this magnetic moment in an external magnetic field. And let's say the system is in equilibrium at some temperature T. The question is, what is the average value of this quantity that appears in the Hamiltonian? So that is the problem, no? So that is the thing that we would like to do. We like to find out how the magnetization depends on the magnetic field, because this Hamiltonian here, the magnetic field factor is there, and it will affect the value of this SI, Z component of SI is going to be, and the system is at some temperature T. Then of course this average value also will depend on what temperature the system is at. So if I can calculate this quantity SIZ average, then I can put it in here. I can find out how the magnetization then depends on the magnetic field and also on the temperature. So this is the calculation that I can work out on the board, and from what your response, it seems that you must have seen it earlier, but you may not recall or something like that. So I'll start with that. And that takes me to this definition of what is called a paramagnet. So to define that, let's just write down here. So basically, I'll say that there is a M is equal to 0 for H equal to 0. I am looking at a situation where only this part of the Hamiltonian is important. Interaction part I'm throwing out. So when H is equal to 0, the energy doesn't depend on whether the spin is up or down. So up and down are going to be equally likely. So when I calculate this average, that will give me 0. Yes? What happens when I turn on the H field? When I have turned on the H field, magnetization in general will have some dependence on H. And that dependence determines whether the material that we are looking at is a paramagnet or something else, diamagnet. That's also a possibility. So to understand that, or to determine which one is the case, you have to look at this quantity, which is called magnetic susceptibility. Determined by this quantity chi, and its typically general definition is that it's and you keep temperature constant. M I have defined here, and we are assuming that whenever there is a magnetic field, your M is going to be in that direction. So that is something that the assumption basically is valid when you have something which is called isotropic system. All directions are equivalent. So if we apply a magnetic field in some direction, typically the magnetization also will be in the same direction. So I don't have to worry about the vector. I look at the magnetization, it's always in the same direction as H. and one looks at derivative that gives you susceptibility. Now, if I want to calculate susceptibility for zero field, if I look at the zero field susceptibility, this can also be written as little m divided by h in the limit h goes to 0. I am starting with zero field when there is no magnetization, and then I am turning on a small value of the magnetic field, then a small value of the magnetization develops, and the ratio of these two also gives you what is called the zero field susceptibility. The value of this zero field susceptibility or sign of this zero field susceptibility is important. Why is it important? It's because in one case the sign is positive. It says I apply a magnetic field, magnetization develops in the same direction as the magnetic field. When these two are in the same direction, then susceptibility is positive. If it is negative, then that means that I apply magnetic field in some direction, magnetization develops in the opposite direction. So these two situations are very different from each other. And so when this, call it phi 0, phi 0 is positive, those materials we'll call paramagnetic. And this phi 0 less than 0, those we will call diamagnetic. Okay, both kinds of materials exist, and we'll look at examples of both of them. So what I'm saying is I'm looking at a situation where there is no sort of spontaneous ordering or anything like that. There is no external field. Magnetization is equal to 0. And then you can define the susceptibility in general as the derivative of this m as a function of the magnetic field. And we're looking at this derivative when the h is very close to 0. And there one looks at two possibilities that one case you are the magnetization is developing in the same direction as that of the external field. Other case it is developing in the opposite direction. And these two cases, they given different names for obvious reasons. One is called paramagnetic and the other is called diamagnetic. So what I am going to tell you now, I mean, I've sort of given you some definitions. The question is, how can one understand how one gets, for example, paramagnetic systems? And I'll also give you some examples of how one can get a diamagnetic system. And in both these cases, I will assume that interactions among these magnetic moments is to be neglected. The reason, I mean, interactions are always there, but we can neglect that when the effect of these interactions are small. And typically in these magnetic materials, when one goes to high temperatures, then the effect of interactions in some cases are small. So high temperatures, one can neglect the interactions and treat the magnetic moments as non-interacting. So that is what we are going to do, but it's an idealized treatment where I'm just saying that there is no interaction among the magnetic moments. It's just the interaction of the magnetic moments with the external field. Given this, do you know which one of these two is realized? You just have a bunch of independent magnetic moments in a magnetic field. Then system will be paramagnetic or diamagnetic. So how many say paramagnetic and how many say diamagnetic? It depends. Because you see that the calculation that I'll be doing is a bunch of localized moments. Let's say if you have a solid and lattice sites, there are ions sitting there, ions have magnetic moment. And this S refers to the magnetic moment of these ions. If that is the case, then we'll get paramagnetism. But if I look at a system of a bunch of electrons, free electrons, each electron also will carry a magnetic moment, right? But it's different in the sense that these electrons are not localized, not sitting at some lattice points. Their wave functions are extended, so they can be anywhere in the system. And there, It can be either paramagnetic or diamagnetic depending on some parameter. There is one susceptibility which gives you paramagnetism, another susceptibility which is called associated with orbital motion of the electrons that gives you diamagnetism. And so it's a question of balancing these two, which one is bigger. So answer is not obvious. The simplest case is where we talk about magnetic moments which are sitting on lattice sites, which are localized. And Hamiltonian is given by this. Then it's a fairly simple calculation to show that that system will be paramagnetic and it will exhibit what is known as this Curie law. Curie law tells you about how the susceptibility depends on temperature. So we'll see, we'll do that calculation. There was a bottle of water somewhere. Thank you. Okay, you are with me till now that we are starting from this Hamiltonian. So then the question is how to calculate this quantity that I just told you about, SIZ, its thermal average. Because that will give you the magnetization, and if you can calculate the magnetization, then from that you can calculate susceptibility, then you can find out whether it's a positive or negative or whatever, how it depends on temperature. All these things can be done. Once you know, given this Hamiltonian, how to calculate thermal average of one of the spins. Right? And this SIZ can have these values starting from minus S to plus S, 2S plus 1 value. S can be either integer or half integer. So, and that calculation is actually one of the first things that one does in what is known as canonical ensemble calculation. So what do we want to do? You want to calculate, for example, the free energy of the system as a function of temperature and magnetic field. And then if you know that, then taking a derivative with respect to the magnetic field, you get the magnetization. And then take one more derivative, then it will give you the susceptibility. And then you can find out how the susceptibility behaves as a function of temperature, as a function of magnetic field. Yes? So let's just do this calculation. So if I want to do this calculation at a fixed temperature T, the starting point typically is a calculation of what is known as partition function. Partition function, if you know, then take the log of that, you will get the Helmholtz free energy. And Helmholtz free energy will be a function of temperature and magnetic field. Take a derivative of that with respect to the magnetic field, then you will get the magnetization. And then you can tell whether the magnetization is positive or negative depending on whether the sign of H. So let's just go through that calculation rather quickly. So we are doing now what is known as a paramagnet, and you're dealing with localized spins. These are SI. And the Hamiltonian is just this. There is a magnetic field H in the Z direction, so the Hamiltonian is just that. So then the starting point is the partition function. Which is given this name, which is this H is the Hamiltonian, Kb is the Boltzmann constant, T is the absolute temperature. So this factor is the Boltzmann factor associated with particular energy state. And this trace, basically, you are summing over all the S. This is sum over Si Z. I can write it as product over I, sum over Si Z takes on all these values, minus L to plus L, 2L plus 1 values. And this trace basically corresponds to summing over all microscopic states. That basically means that for each of the spins, we have to sum over all the possible values this Si Z can take. These are 2S plus 1 values, starting from minus S to plus S. And you do that for all spins. So this is what I mean by that, that you sum over this Si Z values for all I, and that is what one is doing that. So this is the partition function. If you know the partition function, then from that you can calculate what the free energy is, which will depend now on this temperature T and the magnetic field H. And then from that you can calculate what the magnetization is by taking one more derivative and so on. So is there any sort of simplification possible here? You see, the Hamiltonian doesn't involve anything that connects one spin with another spin. These are all independent, right? So when I do this sum to calculate partition function, this I can write as some Z1 raised to the power, because the sums that I have to do, that I can do independently for I equals 1 and then I equals 2 and then I equals 3, etc. In all cases, I will get the same Z1. Is this clear? This actually is the reason why we are throwing out the interactions. If we had the interactions, then the different spins are connected, or they talk to each other. So I cannot do the sum independently. Here, energy depends on the SIZs of the ith spin only for the index I. There is nothing that connects the index I with any other index j. So this sum that I have to do, I can do it independently for each spin. And for each spin, I'll get the same value, which I call Z1. And then this partition function will be the nth power of that quantity, where Z1 and H1 is just for I equals 1. For I equals 2, I get the same thing, etc., etc. So total partition function will be the nth power of the single spin partition function. And this I know how, because H1 involves S1Z. Z can only take these 2S plus 1 values. So this trace, which is basically the sum over all those values, that I can do explicitly. And I don't have to the fact that there are n spins in the problem, because the spins are not talking to each other. So when I look at the partition function, that becomes the nth power of the partition function of a single spin. And the single spin partition function is this, and this sum. I have to put this now in the exponent, and then trace basically means sum over all possible values of S1Z. I know what those all possible values are, and then from that I can get an explicit expression for the partition function for the whole system. So let's just write down what that is. So G mu B H times S1 Z is the Hamiltonian. This beta is a notation that again you are somewhat familiar with, I'm sure. Beta is 1 over KBT. This 1 over KBT is Z. And so basically you will have this, but this S1Z can now have 2s plus 1 values going from minus S to plus S. Yeah. So this gives me Z1. Z1 I can put in there, and simple raised to the power n. That gives me the free energy. That gives me the partition function, and then taking a log of that, multiplying by minus KBT, that will give me the Helmholtz free energy, which will be a function of now temperature and the magnetic field. And from that we can calculate what the magnetization is going to be. Now this is algebra, so I don't know how much algebra you want to do. Let me just do at least the first few steps, and then I'll quote the result. So I'm looking at this Z1. And instead of carrying all these things with me, I'll call that, so G times mu B times H divided by KBT, I'll call some X. So what I'm getting, beta is 1 over KBT. So this is 1 over KBT, this KBT, and then mu times G times mu V times H. G times mu V is called this. So what the sum that I have to do is basically Z1 minus S to plus S e to the X times this whole thing I'm calling X. So X times SIZ, and SIZ has to go from minus S to plus S. And this is, of course, just a geometric series. First term is so first term is e to the minus Sx, then the other term, next term is Siz equals minus S plus 1. That gives me e to the X, etc., and all the way. Eventually, you end up with the upper limit, which is X times S. So minus S is here and 2S is there. This together will give you Sx. So this is something that is simple, right? I mean, one is just writing out the different terms. And then this sum is basically a geometric series, which also you know how to sum explicitly. So basically I get an explicit form for this single spin partition function. Taking it to the nth power gives me the partition function for the whole system. Taking a log of that, multiplying it by minus KBT gives me the Helmholtz free energy. And then you take one more derivative of that with respect to the H to get what the magnetization is. So I will not write down all the right steps. This is something that everybody can do. So basically, I will quote the final result. That itself is a little bit of a complicated expression, but so the different steps I am writing down here. Total Z, Z1 raised to the power n, Helmholtz free energy minus KBT log of Z. Z1 expression I have written down here. and then you have to do this magnetization minus del F del H at fixed temperature. So these steps I am not going to do. I mean, in the sense that you can do the algebra here. F is given, you can calculate because you know how to write down Z1, and then it depends on both H and both temperature, because this quantity X that I have put in here depends on both. And so then you get this F as a function of temperature and magnetic field. Take a partial derivative of that with respect to the magnetic field to get the magnetization. And what I'm going to do is I'm going to write down the final expression for M that you get when you go through this process. When you do the calculation, you will end up with this. I have not told you what this function is. I'm just going to write down this function. So, of course, this is an extensive variable, so it's proportional to n. Then there is this microscopic quantities that tell you about the magnetic moment associated with each of these objects. And then there is this function that depends on h divided by kBt. It depends on h by t because the energy is basically h, and then when you do the Boltzmann probability, then you divide it by kBt. So this combination always comes when you are doing that. And what is this Bs? And it's a complicated function. So you see that this is not a trivial function. S of course comes in here because all the things that I'm doing here involves the spin of these objects that are being considered, and you have a hyperbolic cotangent. This is argument is 2s plus 1 divided by 2s here, and just 1 over 2s over there. So you will get this if you do the calculation correctly, starting from this point. And now it tells you about how the magnetization depends on the magnetic field, how it depends on temperature. So basically, then one has to basically look at how this function looks like when the argument is small, close to 0, or when the argument becomes very, very large, and so on and so forth. So how do we expect? I mean, if you now want to have a result here, if I want to plot this M as a function of H, what do you expect? So when you're doing it as a function of H, you're starting from H equals 0. Field, then H is what? M is 0, right? And then as you are increasing the magnetic field, when the magnetic field becomes very, very large, then what do we expect the magnetization to be? You see, the energy is minimized when the magnetic moment is in the same direction as the magnetic field, right? So at very, very high magnetic fields, what do we expect? What would be the value of SIZ if H is very large? Somebody say something. What is the maximum value that SIZ can have? Yes, right. So when the field is very large, then all the spins will be aligned, or all the magnetic moments will be aligned with the field, and SIZ will have the maximum possible value. So it will then saturate at a value where all the spins SIZ is equal to plus S, where magnetic field is in the H direction, in the positive direction. So I mean, without actually plotting this function explicitly, I can determine. So when there is no magnetic field, there is no preference as to plus S or minus S or whatever, positive or negative direction. So as I said, in a paramagnet, this starts from 0. And then when H is become very large, then this will be somewhere given by, magnetic moment is given by G times mu B G times mu B times S. N is total number of spins, so I'm looking at the small m, so I'm dividing this big M by the big N, so it's the magnetization per spin, and that will saturate at some value where, so I mean there will be some picture like this. And if you actually plot this out, then you will get this kind of a graph, which looks at essentially like that can never be, it will tend to saturate at a value which is G times mu B times S. And that you can verify explicitly. If I put this H equal to 0, the argument here, this Y, basically we have to look at the value of this or behavior of this function when Y goes to 0, and this function's hyperbolic cotangent, you can work out how this function looks like when the argument goes to 0. And explicitly one can show, I mean, from this formula that M will be 0 when H is equal to 0. And similarly, if I now look at this Y going to infinity limit, when this H becomes very, very large, again, one can look at the asymptotic behavior of these hyperbolic cotangent functions, and one will find that that goes to 1, basically. So you will get G times mu B times S as the value of the magnetization per spin when the magnetic field becomes very large. So that's one thing. But you see, the argument here comes as a ratio of H divided by T. So if I look at, for example, some positive value of H as a magnitude, but T very, very large, temperature very, very large, then again the argument here is going to 0. And so there also we'll start with the value of M, which is going to 0 as T goes to infinity. And when T becomes very, very small, then this argument becomes large, and the magnetization will then go to a saturation value. So this is how this material, which I have assumed that to be localized spins and they are not interacting with each other, its magnetic behavior then can be calculated simply just by an exercise of statistical physics in some sense, that you calculate partition function. Partition function you can calculate because they are not interacting, so you have to just look at the single particle partition function, raise it to the power n to get the full partition function, and then yes.